Hi, welcome to Lesson 16.2, Limit Theorems, Part 1 of 2. So there are theorems that we have to kind of follow so that we can find out more shortcuts and tactics to solve or find limits, okay? So here's the first part 1. So if f of x is equal to a constant k, then the limit as x is approaching c, whatever number that is, of f of x is going to be k. So in simpler terms, I will give some examples, verbal examples. So let's say the limit as x approaches whatever, doesn't matter, 5, 10, 100, 1,000. So as the limit as x approaches a number of, let's say, 10, then my final answer is 10. Okay, hopefully you see a pattern. The limit as x approaches 500 of a function such as 2. My answer is 2. The limit as x approaches -5 of 8. My function is 8. Then my whole limit is 8. So again, if you're given a constant function, so just a number, then the limit of that function is a constant. So that's pretty easy, I hope. So the limit of a constant is a constant. So the limit of 5 is 5. The limit of 10 is 10. The limit of -2 is -2. Okay? The second one is where you have a polynomial, basically, where you have x to the power of anything. Make sure that anything is a positive real number. Then all you do is really just plug in that number. That's really easy. You learned that in the past part 16.1. where you're plugging in. So the limit as x approaches a number, doesn't matter what number, as long as it's a number, of let's say x to the 5th power. Then you plug in whatever the number they give you to the 5th power, and boom, there's your answer. So for instance, the limit of x approaching 5 of x squared is going to be 5 squared, which is 25. Okay, another question is limit as x approaches 8 of x squared would be 8 squared, which is 64. Okay, so the limit of x to the power is the number to the power. Okay, so let's see, two truths and a lie. So the first part A is just like bullet number 1, where the limit as x approaches 3, your y is 10. So that is forever 10. So your limit of a constant is a constant. Doesn't matter what the x is. No matter what x you ask for, your answer is 10. So that's the truth. Part B, that's like the second bullet, where it is a polynomial and you're going to plug in that -3 into your x. I think that might be a problem because I'm noticing that -3 to the power of 3 is not 27. Let's just check letter C one more time. So letter C is the second bullet where you plug in 2 into your x. 2 to the 5th. I think that's correct. That is 32. So for the first one, part A, that's correct. Last one, part C, is correct. However, letter B is incorrect. The answer should have been -27. Okay? So rule of thumb, if it's a constant, the limit of that constant is a constant. If it's a polynomial, the limit of that polynomial, you plug it in, okay? All right. Now, these are some theorems where it's saying that, let's say one function, there's a limit. It approaches, let's say, 5. And another function exists, meaning, let's say this approaches 8. Okay, and they are two separate functions. Notice f of x and g of x. They're two different graphs. Separately, they exist. So now, if we had to combine them, then that means this will be the limit of a sum is a sum of limits. Now, I think this is a typo. This shouldn't be there. This letter G is not there. Okay, but what it's saying is, you can take them individually, take the limit of the first function, find an answer. Take the limit of the second function, find the answer. But that's very tedious. So rather than doing that, just get the original functions, put them together, and just find the limit of that, meaning plug in. Okay? The next one, you have a limit of the difference, and that's individually taking the difference of the limits. So it's equivalent. No matter what you do, whether you do it separately and subtract after, or subtract the polynomial and take the limit of the whole thing, it's going to give you the same answer. Okay, this one's the product, so if you multiply your two original functions together and then take the limit, it's the same thing as taking the limit individually and then multiplying at the end. And lastly, taking the quotient of your two functions first, then taking the limit is the same as finding the limit separately and then dividing. So again, the typo, these are not supposed to be letter G's. I think those are supposed to be little bullet points. Okay, don't get those confused. All right, so I would recommend doing the left side because that's a little bit shorter. You don't have to find it twice and then add them. So it's better to combine the functions first, then take the limit. My word of advice. Okay, so if we take a look at this polynomial, you can do it the long way where you're doing part of a limit plus another part of a limit times another part of a limit minus another part of a limit. That's a lot. Okay, I'm going to show you the tedious work. So this is not advisable, but I'm just showing the work. We're going to take it individually like we saw in the theorem. We're going to take the x squared, find the limit, take the limit of 3, take the limit of x, then take the limit of 5 and do the math operations after. So limit of x squared is 2 squared, so 4. Limit of 3 is always 3. Limit of x, plug in the 2. And then limit of 5 is always 5. So now it's just purely mental math, and that will result to 5. Okay, so that is a lot of writing. So here is what I recommend. Instead, go just straight through and keep it like this whole thing, and just plug in the 2 into your x. So 2 squared plus 3 times 2 minus 5 should give you the same result of 5. Just two ways of doing it. The bottom is quicker, more efficient. The top is taking them all separately, finding them separately, and then doing the math operations. Two ways. All right, so try this one. Example 2. Find the limit as x approaches 4 of this function. So we technically have f of x on top, g of x on the bottom. We're taking the limit of the quotient, which is the same as finding the quotient of the limits. Okay, so I would rather just straightforwardly plug in, see where that gets me. So I have 4 squared plus 5, the denominator 4 squared minus 2 times 4, and that will yield to 21 over 8. So look at that. That was a lot faster than taking them individually. That would have taken at least 4 or 5 times to do, 4 or 5 times longer. All right. So now there are occasions when your limit, when it's asked to find out a specific value, like x is approaching 1 or x is approaching 5, where when you plug in, you're going to get undefined. So there's only two answers after that. Either it does not exist, your limit doesn't exist, there's no such y value that matches, or you could find a y value that matches. Okay, so let's take a look at the first one. If I were to go straight forward, plug in -2, I'm going to get an error. It will end up being +1 on the top and 0 on the bottom, which means 1 divided by 0 undefined. That's not possibility. So I have two choices. It's automatically does not exist, or it would be I have to do some algebra and then plug in after. So in this case, unfortunately, I can't do any algebra, I can't factor, I can't cancel, I cannot do anything to this. If you think about the graph, this is where you have your horizontal asymptote at y equals 1, your vertical asymptote at x equals -2, and you're going to have these two curves in the first quadrant and the third quadrant. So what's happening is You can graph this in your Desmos as well, and then also a graphing calculator. So at -2, there's a discrepancy. So let's actually see this on Desmos. So let's open up Desmos and let's type it in. So f of x equals, the numerator was x plus 3, and the denominator was x plus 2. And let's look at -2. So here's where -2 is on the x. And if I were to be asking you what's the limit from the left side, so here's the left side, and if I get closer and closer to -2, then that means the y value is just going to keep going to -infinity, okay, the y value. But then if I ask what's the limit from the right side as you get closer to x equals 2, and this continues to rise, so that means your limit for the right side is +infinity, just keeps going. So there's a discrepancy. At x equals 2, there are two y values that are approaching it. Therefore, there is no limit. So that's why, for this scenario, the limit does not exist. There are two y values approaching -2. From the left side, it was -infinity. From the right side, it was +infinity. They don't match, so the limit does not exist. DNE. Okay, we couldn't do any algebra. However, for part B, this case, we plug in 2, so we're going to get top is going to be 0. Uh-oh, the bottom is 0. That's still undefined. However, I can factor. So I'm going to do algebra, the magic. So the top, I'm going to get a difference of squares. Don't forget to copy the limit, LIM, as x approaches 2. We're not done yet. We can't get rid of the word limit until we actually plug in. So now I'm going to cancel out the x minus 2's, and I'm left with this right here. Still keep the word limit in front. Now I could plug in. So 2 plus 2, now I don't need the word limit, and that equals to 4. So in this situation, I was able to find the limit by doing some algebra, by factoring, by canceling out, so that I will not get undefined. So I hope that makes sense, where you can either say the limit doesn't exist at that spot, or the limit does exist and it will be a number. So again, limits are never exact, all right? It is always just approaching that number. So maybe like 3.999 or 4.0001, right? This is an approximation, limits. All right, on to the next.